Okay, today we will move to uh, the class activity today, that is in the topic of initial value problem, that we will apply the Euler method, Huon method, and midpoint method to solve the basic differential equation, ordinary differential equation, as shown as the example of this problem. And for the case that the equation is maybe more complicated, but in order to verify the result, we will use the basic equation. But actually, this method can apply for a case that the equation is more complicated, that is maybe nonlinear, highly nonlinear equation we can apply to solve. Okay, but today we will just show you that the method of Euler, Huon, and midpoint can perform to give us the results of differential equation, how and the precision of the result that's obtained from this method in comparison with the exact solution is what's happened to that. Okay, and in order to understand the concept of the numerical method for solving ordinary differential equation first, and then we will move to the more powerful method, that is Runge-Kutta method, that is give us very close solution to the to solve the differential equation. Okay, so it's just a little bit review. We know that when we have the equation in this topic, we would like to solve the equation in form of dy by dx equal to fxy. Okay, if we have the equation in this form, okay, so we can solve based on Euler. Euler is yi plus 1 equal to yi plus initial slope, that is represented by fxi yi multiplied with h. Okay, but for Huon we have to do two steps. That is, in order to find the final result, that is yi plus 1 equal to yi plus the average slope, okay, multiplied with h, and the midpoint is yi plus 1 equal to yi plus the slope at mid-step, multiplied with h. Okay, actually the term of average slope and slope at mid-step actually is we can determine by using the function fxy, because as shown in this equation, we know that fxy represents the slope of the curve y. Okay, so we may starting with the Euler method first. For the Euler method, we would like to solve this problem from 0 to 2. Okay, and initial value is at time equal to 0, at t equal to 0, y0 is equal to 1. We know the initial value already. Okay, so for the Euler method, okay, we may starting with the Euler method. That is, what is it? We may create a table like this. Okay, for the Euler of step size h equal to 0.5. Okay, we just So for the example of s equal to 0.5 by hand, and after that we may step to the Excel for solving by or solving with step size of s equal to 0.25. Okay, for time equal to 0. Okay, and if it is equal to step size is if s equal to 0.5, so then time is become 0.5, 1.0, 1.5, and then 2.0, right? Okay. Okay, then we have the equation of dy by dt equal to y t cube minus ay. A for you, a represent your key number, right? Okay, but for me, I would like to use a as 1.5 because I have the solution already. Okay, in order to go faster, because actually we have the limit of time, we should go to this topic, and then we will move to next topic if it's possible. Okay, so the equation I give that a is equal to 1.5, but for you have to use a as the key number, your key number, right? Okay, and this is the 1.5 y. Okay, and then so what does it mean? It means that fxy is equal to this fxy. For this case, it's become fty. Fty is become yt power 3 minus 1.5 y. Okay, so according to this, and initial value that we have is at time equal to 0, y0 equal to 1. Okay, so when time equal to 0, y equal to 1. It should be y. Okay, and for s equal to 0.5. Okay, for this case, and at time equal to 0, this is equal to 1. This is the given value. It is the initial value. Initial value is given from the problem. Actually, for the problem that we would like to solve, for the real problem, we should identify what is the initial value exactly. Okay, from our data, from the condition that we would like to forecast, we should know what is the initial condition for our problem. Okay, so for this case, that is the example, we know that the initial condition is when time equal to 0, y0 equal to 1. After that, we do next for the time step, that is when t equal to 0.5. That is, we would like to find yi plus 1. Okay, that is equal to yi. Okay, plus if we use Euler first, or the Euler, if we use Euler first, for the Euler yi plus fxy. Multiply with h. So yi is become what? For this case, yi is 1, right? Because we have to use the initial value, and then plus fxy is equal to, sorry, for this case I should write fty. t is equal to 0. So for this case, what is it? Y is equal to 1, right? T is equal to 0 minus 1.5. Y is equal to 1. Multiply with h is equal to 0.5. Okay, so what is it? So this should be negative, right? So it's become 0.25. Okay, now we have 0.25 here. Okay, then do next. For next step, okay, for next step, when time equal to 1, okay, when time equal to 1, so equal to what? We have to use this as the initial value for next step. 0.25 plus, okay, 0.25 multiplied with 0.5 cube minus 1.5 multiplied with 0.25. Okay, you understand? After that, what is it? We get the value of 0.078125. Okay. Okay, now do you understand? Okay, are you okay for the example for the Euler method for this case? Are you okay? If no question, do you have any question for the Euler? If you have no question, okay, we will move to next method, and then before we move to next method, I will create the Excel sheet for this problem first. Okay, but before we do that, we should solve for exact solution first. This equation is the ordinary differential equation of the first order, and it is the linear equation. This is a linear equation. According to this equation, when we solve analytically, if we would like to find the exact solution, for the exact solution, exact solution means that we have to solve the solution, the equation analytically. So in some case, we may not have to solve by ourselves if we have the solution from the mathematical handbooks. Okay, we can use the formula that we already know. For that case, that is okay also. I actually in my opinion, I think when I for the problem in the exam, I think it can solve by hand. You may use your basic knowledge in mathematics to solve exact solution. Okay, and the solution that obtained from the calculator, for example, like the exam that someone that use the calculator function integrated, and you got the solution that actually it is very close to the exact solution, but actually I told you many times it is not the exact solution. It is a numerical solution that's obtained from the calculator. Okay, so if you do like that, so I know. So it means that you not reach the target that's for the problem that is would like you to show. Okay, so if the problem that's given that you have to determine the exact solution, you have to show a little bit that what is the exact solution in the formula case, what is the analytical solution that it should be shown in the equation, show by equation first, and after that you have to show that you use that equation to solve the solution. Okay, but someone that is give the wrong solution, give the wrong analytical solution, but you got the correct one. What does it mean? It means that you have the tricky is you trick something. Okay, you don't know how to solve, but you use your calculator to obtain the exact solution. That is it is not good. Okay, so for the exact solution from this case, we can rearrange the equation to be like this: dy by dt equal to y multiplied with t cubed minus a. For this case, a is 1.5. Okay, so according to this, we can separation of the variable 1 over y dy equal to t cube minus 1.5 dt. Okay, according to this, we can integrate both sides, and we got log y equal to t power 4 over 4 minus 1.5 t. Okay, plus c. Okay, plus c. We have a constant also. So according to this, we have the initial condition. For the initial condition that we have when time equal to 0, y equal to 1. Okay, so when we substitute the initial condition to this equation, because we have the unknown that we have to solve, c. Okay, so when time equal to 0, we have y equal to 1 equal to 0 power 4. Okay, plus c. So that's mean it means that log 1 is equal to 0, right? So it means that constant is equal to 0. Constant is equal to 0. So then it means that we have the equation of log y equal to t power 4 minus 1.5 t. Okay, and if we would like to rearrange to be y is become the exponential of t power 4 over 4 minus 1.5 t. Okay, this is the exact solution. You have to show this. If you do not have this equation, it means that you don't have the exact solution. Okay, so now we have the exact solution already, right? And then we already understand the Euler method. So we will create the Excel sheet for show us that what happened if we use the step size is to for the smaller case. Okay. If we use the step size in different step size, and what happened to that? Okay, so for the case of this, we should develop a table like this should be t, okay, and this should be yt. Okay, we may starting with the exact one. We may starting with the exact solution first. Step size is equal to 0.5. We're starting with step size of 0.5. And the exact solution is what? This is the exact solution, right? That we already done. Okay, exact solution is equal to exponential of, okay, e power 4, e power 4 over 4 minus 1.5 e. Okay, so now we have the exact solution of at the first point, that is actually it is the initial condition. It is the same value of initial condition. Okay, we do until time equal to 2. Okay, and this is the exact solution. After that, we will move to the Euler. This is for the Euler method. We have the equation of this equation. So we may starting with h equal to 0.5. Okay, and this is y. So starting with initial condition should be given. That is equal to this. This is initial condition. So this rho is not necessary to calculate because it is an initial condition. It should be equivalent. Okay, and then if we would like to determine the y, we determine the value of y in next time step. So what is it? yi equal to fxy h, right? Okay, now we know that h is equal to 0.5. And so for this case, it's equal to this value, right? Because we know that from the Euler, we have this equation, right? Okay, so this is what? This is yi. Yi is the initial value, that is the value from last step, plus fxy. Fxy is, for this case, fxy is y, that is the value from the last step, multiply with time ti, that is time at the last step, power 4, right? Okay. Oh, sorry, power 3. Okay, minus a, for this case is 1.5. Okay, multiply with y. Multiply with y. For this case, a is 1.5. Okay, 1.5. Multiply with y. Y is this value. Okay. So we got the solution of this. Oh, sorry, we have to multiply with h. Multiply with h. H for this case is 0.5. Okay, got this. Okay, after that, we do the same thing. Okay, we do the same thing. Okay, when we move to this, we use the value at time step of 0.5 as the initial value and do the same thing for next step for time equal to 1. Okay, then we got the solution like this for the case of Euler with step size of 0.5. Okay, with step size of 0.5. Actually, it should be better if we do something, because Excel is maybe can do anything better than this. Okay, for example, I may copy this table to here, and I will identify the step size. I will identify step size over here. It should be h size. Maybe fill in this. Okay. So if I given step size of 0.5 over here, so it should be okay. Okay, and the exact one, it should not necessary to correct, and for here it should this should be, it should be here. So now okay, this is for step size of 0.5. Okay, if I do the same thing with step size of 0.25, sorry, is for step size of 0.5, right? Okay, so I will use this table to solve for h that is maybe not step size of 0.5. Okay, but I have to collecting the solution of 0.5 first, but actually we already have. Now we move to the time step of 0.25 as the problem that would like me to do. Okay, we have to solve for h equal to 0.5 and h equal to 0.25. So for this case, if we given h equal to 0.25, so the solution should become like this, and then we should do next until t equal to 2. Now we have the solution of h equal to 0.25 already, right? Okay, we have the solution of 0.25 already. This is initial value. And after that, if we solve the solution, that's if we would like to conclude the solution for this problem first, it should be what? It should be like this. And if we would like to compare the solution with step size of h equal to 0.5, and h is equal to 0.25. The solution is what? We should not have the solution rate for the case that h equal to 0.5. We should have this value instead. In conclusion of the result, we have this, okay? And if we would like to find the percent error in comparison with the exact one, we search for percent error for h equal to 0.5 first. And then this is a percent error for h equal to 0.25. Then it should be 0% because it is the initial value that's given from the problem. For the percent error is the absolute value of the exact solution. Oh, sorry, for this table it should not have. We have to find the percent error with respect to the exact one. So we have is the error is of 18%. Oh, sorry, it's not correct, so it should be here. Oh, sorry for that. I copy the solution of the exact to the solution of the Euler. Sorry for that. It should be the solution of the Euler, not the exact. Okay, now you see that the error from the Euler solution from the Euler method become 47.89%. Okay, it's too high, right? So if we reduce the step size, what's happened? If we reduce the step size to 0.25, what is this? The solution is become Okay, so the percent error is reduced if we compare with at the same point, at the same step size. You see that the step size, the reduced in step size, we obtain the better solution, right? But for the final time step, you see that it still have the error, a lot of error also. Okay, so this is the Euler method. This is the example of the Euler method. Okay, so this is the first one for Euler. So what happened if we use the step size is smaller than 0.25? So if I use step size of 0.05, what happened? 0.05, what happened? So what do you think? If I use the step size, it's maybe just 0.05 is the percent error. Okay, you will find that the percent error is maybe reduced, but what happened to next when the final solution that we would like to find? What happened? We still have the huge value of error also. Okay, in comparison with the exact solution. Okay, because in each time step we have the error, and the error is cumulative. Okay, until we reach the value that we would like to find, we will found that it has the error of 34%. So that's why the Euler method is not good enough to solve the problem, but it is easy to understand. Okay, it is just the basic. It is just a concept. Okay, so now do you understand for this case? Okay, for the case of Euler first. Okay, do you have any question? I will stop the clip for this case first, and then we move to Huan and midpoint.